I want to give you a little help in writing a flowchart and your net ionic equations for this Qualls-Keymes separation. So here, I've just got part of the procedure from the article. It starts with putting your unknown in a test tube. And so here we have all of our ions possible. And it says add 2 drops of 6 molar nitric acid, 1 mil of 6 molar ammonium hydroxide. So I've written that in here. And then you're going to stir it and centrifuge and decant. So it's possible to have a solid form, and of course you'll still have an aqueous phase. In the solid, you're going to have the group A ions. So here's the group A ions, those are in the solid. And so over here in the aqueous, we have everything else. And it's going to be groups B and C and the magnesium. Here's group B, here's the magnesium, and there's group C. Those are still in this aqueous phase. So then we take the group A solid and we add 1 mil of 1 molar sodium hydroxide. Stirring, centrifuge, and decant. To the solution, add acetic acid until slightly acidic. A white precipitate indicates aluminum. So we took this solid and we added sodium hydroxide, and some of the solid may have dissolved, and that would be the aluminum. The ions that did not dissolve will just remain in the precipitate, and those will be the iron and the manganese. So here then we're taking that, the aqueous phase containing the aluminum ion, we're adding some acetic acid until it gets acidic, and then we may see a precipitate. A precipitate will confirm that we have aluminum in our unknown. What's in the aqueous phase? Just leftover stuff. There should be no ions present there. So this is just a little taste of how you might go about writing the flowchart. Then we also need to write net ionic equations for all of the chemical reactions that occur. So let's remember that a chemical reaction is evidenced by the formation of a new compound, formation of a solid from the mixing of aqueous solutions, formation of a colored substance or a change in color, formation of bubbles, and then heat absorbed or released. So every time we come to a branching point, like here, we have a solid formed. There's some chemical reaction that occurred to form that solid. Nothing happened here in the aqueous, it just remained aqueous. So we need to figure out, okay, what is precipitating here? What are the ions that precipitate? Well, those are the group A ions, right? So that's these guys right here. So we're going to have aluminum, and these were all originally aqueous. We're going to have iron, and we're going to have manganese. So we're adding something to those, and we're getting a solid that forms. So we need to figure out what is the solid, what's the other reactant. Well, let's look at what we added. We added nitric acid and ammonium hydroxide. So nitric acid will ionize and form hydrogen ions and nitrate ions. We're looking at things that are going to react with a cation. Hydrogen ion is also a cation. Those aren't going to react. Could it be a solid formed with nitrate? If we look at the solubility rules, we see that all nitrate compounds are soluble. So that rules out the nitrate. Let's look at this one. We have ammonium ion and hydroxide ion. Again, ammonium ion is a cation, so that's not going to react with other cations. So it must be the hydroxide. So put hydroxide in here. The hydroxide is aqueous. And what's this going to form? Well, it's going to form a solid, right? And so that must be a neutral compound. So let's write the formula for a compound that forms between aluminum and hydroxide ions. And so that's going to be AlOH3, solid. And then we need to balance that equation. Do we need to show the ammonium in there? No, we don't. We're looking at net ionic equations. Sorry, that's my vacuum cleaner. Okay, so that's one of them. What about the others? Well, there's also the iron and the manganese. Well, those are also reacting with the hydroxide, and so you can write an equation in the same way for the formation of iron hydroxide and manganese hydroxide. So let's look at what happens next. We take this solid and we add sodium hydroxide. Some of this remains a solid and some of it dissolves. We know from the instructions that what dissolves is the aluminum. So that means that this AlOH3 that was formed must be dissolving and forming something new. So AlOH3, solid. And what are we adding? Well, we're adding sodium hydroxide. Again, it can't be the sodium, must be the hydroxide. So we look at this and we're going, what? How is this going to do anything? This is where it's important to understand or to remember that aluminum does weird things. Okay, so there's a section in the book that talks about this, about the pH-dependent solubility of aluminum and how it forms complex ions. So as it turns out, if you go look that up, in a high pH solution, this solid here will pick up another hydroxide ion and form a complex ion. And that will have the formula AlOH4 minus. I do not expect you to know that off the top of your head, but your book is a resource and you can go and look that up. So is that a balanced equation? Yeah, yes it is. Okay, then what happens next to the aluminum? So we see that here we've got a solid formed, there's chemical reaction happening. Here we have a solid that remains and an aqueous, again, chemical reaction occurring here. Now here we have that aluminum, and again, we're having some change occur. So here we're adding acetic acid until it's acidic. Well, what's going on here? So adding hydroxide made this soluble. If we're adding an acid, what's that going to do to those hydroxides? It's going to begin to neutralize them, right? So this is actually just kind of the opposite happening. So if we're adding hydrogen ion to this, now we're going to get our OH3 solid back plus H2O. And I did the aluminum equations for you because those are really the trickiest. They make the least sense. But hopefully this gives you an idea of what you should be doing as you go through. And another tip here is the total number of equations. You should be able to find 19 net ionic equations. Hope that helps.